Welcome back, fellow mitochondriacs, to another episode of Cancer as a Mitochondrial Metabolic Disease. Oxygen is fundamental to life and to the energy our cells produce in mitochondria. Most assume the oxygen level in our tissues is about the same as the air we breathe. But in reality, most cells in your body live in a much lower oxygen environment. Cancer cells don't live in the same oxygen environment as the rest of the body. Many tumors grow in regions that are severely oxygen deprived, and that changes everything about their metabolism. Today, we're going to discuss the oxygen status of normal cells and that of cancer cells. So without further ado, let's get into it. Okay, I've decided I'm going to break this topic into several different videos, probably two or if not three videos, because it's so critical for us to understand this moving forward, because a lot of the oxidative therapies, as you can imagine, require oxygen. Okay, so we're going to take a look at how normal tissues differ from tumor tissues of various types, and then we're going to see what that hypoxia does to our chances of having success with therapies. So I'm going to start out with a paper that came out in March of 2014, and it's probably the best paper on the subject that I could find. And it's titled Defining Normoxia, Physioxia, and Hypoxia in Tumors, Implications for Treatment Response. And it says tumor hypoxia is increasingly recognized as a major deleterious factor in cancer therapies, as it compromises treatment and drives malignant progression. This review seeks to clarify the oxygen levels that are pertinent to this issue. It is argued that normoxia, 20% oxygen, is an extremely poor comparator for physioxia, i.e., the much lower levels of oxygen universally found in normal tissues, which averages about 5% and ranges from about 3 to 7.4%. Importantly, it should be recognized that the median oxygenation in untreated tumors is significantly lower, falling between 0.3 and 4.2% oxygen, with most tumors exhibiting median oxygen levels of less than 2%. This is particularly dependent on the tissue of origin, and it is notable that many prostate and pancreatic tumors are profoundly hypoxic. In addition, therapy can induce even further, often unrecognizable changes in tumor oxygenation that may vary longitudinally, increasing or decreasing during treatment in ways that are not always predictable. Studies that fail to take cognizance of the actual physiological levels of oxygen in tissues, approximately 5%, and tumors, approximately 1%, may fail to identify the real circumstances driving tumor response to treatment and or malignant progression. This can be of particular importance in genetic studies in vitro when comparison to human tumors is required. So let's take a look at the graphic, or at least one of the graphics, that is associated with this paper. And so there's kind of two different ways of looking at oxygenation, and you'll see this in the medical literature. And I would say probably more often than not, it's going to be using partial pressures of oxygen, which is labeled in millimeters of mercury, but also percent oxygen. So right now, all of us are breathing 21% oxygen, unless you're, wearing supplemental oxygen right now via nasal cannula for some, chronic condition like COPD or whatever. You're going to be breathing 21% oxygen. And then what happens is that by the time it actually gets into the lungs, it's about 13.5%. By the time it actually gets into the bloodstream, it's about 9.5% oxygen. By the time it gets to the end of the arterial circulation at the venous end, it's going to be about 6.5%. And then when you look at what most of the tissues are getting, it's on average, like the abstract had mentioned, about 5%. That's why for 5% is proposed as the compromise, because it goes anywhere from like 4 to 7.5%. So 5% oxygen corresponds to 38 millimeters of mercury. Okay, so these two are equivalent. Now, when we get down to physiological hypoxia, that's the low end of normal of what you can actually handle to use oxygen effectively. Then that would be about 2% oxygen or below, and about 15 millimeters of mercury. Okay, so these are very, very important numbers to be aware of. Okay, because what we'll see is that most tumors are much lower than this. So here's pathologic hypoxia, 1% or 8 millimeters of mercury. This is like very hypoxic. And then there are even lower levels of hypoxia, which make them very, very resistant to treatment. And we'll look at those. So let's take a look at one of the other cool tables that came up with this paper. And it basically has multiple tumors, right? Here's maybe GBM, glioblastoma, or some kind of astrocytoma, maybe head and neck cancers, lung cancers, breast cancer, cervical cancers. It happened to mention in the abstract pancreatic cancer specifically and prostate cancer specifically at having ultra low levels. And it gives the mean tumor PO2, right? So this is the average, basically, oxygen level in millimeters of mercury. Okay, here's millimeters of mercury. And then this is the median oxygen in percent. So what we get here at the end is an average of all of these types of tumors. And the average in terms of percent is about 1.4% oxygen, which corresponds to 10.27 millimeters of mercury. Now, this is not actually even giving the entire story because, and I don't have a graphic for it here, I probably should have put one in, but there's like a tumor architecture of these solid tumors. And the tumor architecture is generally such that the outer layers of cells, usually the rapid proliferating cells, are in a higher amount of oxygen, right? So they may be slightly higher than 10%. And then in the deeper cores of the tumor, where a lot of times the cancer stem cells are at, those are generally considered poorly vascularized and much more hypoxic. So again, this is the average. And then if you actually look at the conclusion here, it says tumor hypoxia is a critically important parameter, which compromises treatment and promotes malignancy. We're going to look at that in detail in a minute, or in the next couple of videos. It is widespread in human tumors, and it has a marked effect on responses across most treatments, irrespective of the mode of action. That could be chemo, that could be radiation, immunotherapy. We'll see that in greater detail in the future videos. In experimental studies, it is crucial that investigators control for oxygenation to mimic, as far as possible, the significant low oxygen levels found in most human tumor cells. That is at less than 1% and often less than 0.1%, which corresponds to 7.5 millimeters of mercury on the higher end to 0.75 millimeters of mercury on the low end. Now, before I get into why this is important, specifically for oxidative therapies, which is what this series is about, I want to take a little bit of a detour for a second, okay? I wasn't going to do this in this order, but I think it makes more sense now that I'm actually reading off these slides. So, mitochondria use oxygen to make energy. As a matter of fact, 90% or more of the oxygen that we breathe in ends up as the terminal electron acceptor in mitochondria. It's all used by mitochondria. And that mitochondria use it for one reaction right here at complex 4, oxygen making water at the very end here. Now, there are studies of particularly heart muscle cells that if you decrease the oxygen for these heart muscle cells from normoxia or physioxia, which is defined as being somewhere in the 38 millimeters of mercury, right? 30 to 40 millimeters of mercury range, or 5%. Then when you lower the oxygen levels to 10 to 13 millimeters of mercury for just 30 minutes, it decreased the mitochondrial output of energy by 50%, which makes a lot of sense, right? Because if they normally are living at 30 to 40 millimeters of mercury, and you have the amount of oxygen that is available to these mitochondria, it would make sense that the work that they do or the output of energy that they put out is 50%. So, knowing what we know about mitochondria, about oxygen, about how sensitive they are to low oxygen or hypoxia, then let's take a look at what the average tumor is, somewhere between less than 1%, even as low as 0.1%. So when someone tells you that, let's just look at prostate. If someone tells you that prostate cancer is burning fat for fuel or ketones for fuel, or it's metabolically flexible, you'll see here that most prostate cancer lives at about 0.3 to 1.2% oxygen, which is about 2.4 to 9.4 millimeters of mercury. And that's as a median, right? That means there's hypoxic regions of those tumors that are even much lower than that. How is OXPHOS, which is what is required to be functional, to burn fat, to burn ketones for fuel going to be operational at all in that cancer? Make that make sense. If someone can explain that to me, I'll concede. But as of right now, this basically, without a shadow of a doubt, proves that these cancer cells, even if the mitochondria were functional, let's say Seyfried's completely off base, these mitochondria structure, number, function, they're all normal. They're beautiful cristae. The level of oxygen in these tumors prevents these mitochondria that are beautiful, supposedly, and intact, supposedly, from using oxphos. Now, I made that point because it's just a point that begs to be made at this point in time, okay? But this particular series is not about whether cancers can burn fat for fuel or ketones for fuel. We've beat that horse to death already multiple times, and it still comes up over and over again. So I just try to make the point whenever I can, because it's sometimes maddening, and I'm not really per se mad at people, because this is a difficult concept to conceptualize, and you have to understand the underlying physiology to understand why it doesn't make sense that these cancers are burning oxygen through mitochondria, et cetera, and burning fat and stuff like that. But since this is a series about oxidative therapies, then what I'll also mention is that the reactive oxygen species that we are trying to generate in high amounts to kill cancer cells are completely dependent on the amount or quantity of oxygen. So all of these reactions, these Fenton reactions, and these Haber-Weiss reactions that make the hydroxyl radicals or peroxides or the superoxides, all of those oxygen-free radicals, as you would imagine, require oxygen as the parent compound before those reactions can be created. So therefore, it is well known that the standard of care treatments, specifically chemo and radiotherapies, are exquisitely sensitive to the tumor's oxygen status. As a matter of fact, I'm going to spend a great deal of time talking about how oxygen status in tumors limit effectiveness of the standard of care. And you're going to see graphics like this and other graphics that prove that point. So this is a graphic that shows the relationship between tumor oxygenation and radiosensitivity. And it says here basically that the lower the oxygen in the tumor, the less chance for the radiation therapy, blasting it with radiation, is for it to have an effect at killing those cancer cells. Because if there's no oxygen, the amount of reactive oxygen species created by radiation therapy is not going to be effective. And this has been known for a long time. I mean, this paper was published, in 2014. There's other papers we're going to look at that show very similar things. So this is very well known within conventional radiation oncology, yet we still have not really addressed it. We're still shooting people with the same radiation, but we're not addressing the underlying cause for its failure. And we're going to look at maybe some strategies that could be potentially used in the future in this series to potentially enhance even the standard of care, chemo and radiotherapy, by knowing these important concepts about tissue oxygen status. So if you like videos like this, please like, share, and subscribe. And until next time.